Good afternoon, everyone. In this lecture, we will be talking about the combinational logic analysis, and mostly we are going to use the logic gates in order to analyze the logic circuits. For example, here we've got AND OR logic. That means those logic circuits which are composed of only AND and OR gates. So in here, we've got two AND gates and we've got four inputs. Each two inputs is connected to an AND gate. The output of each AND gate is connected to the input of the OR gate. So as you can see, here we've got two ANDs which are ORed together, or we can say the sum of products. So by the end of the circuit, at the output, we will be having A and B sum or C and D. So we will be generating sum of product. So this is what is called logic diagram, but this one is a rectangular symbol. Like for example, those AND symbols are referring to the AND. So that means the A and B are ANDed together and C and D are ANDed together. And this is greater than or equal to 1 is corresponding to OR gate. That means that AND gate and that AND gate are ORed together, and this is going to be the final result. So at the end of the result, we will get a sum of product. Like what do we have here? So they are the same, they are similar to each other, but this one is logic diagram and this one is rectangular outline symbol. So this is the opposite of the previous one. We've got AND, OR, and invert logic. The circuit is the same, except we've got a NOT gate by the end of the circuit. So this is going to be a NOT gate, or you can say only a bubble here instead of that one. So you've got AB or CD, and we are going to invert that one. And that inverter is going to go above the whole expression because the NOT gate is after the logic gate. So if we apply the Demorgan theorem 2 times, we will get that one. So if we convert that one into rectangular symbols, we can say A and B, C and D, and they are all together, and that slope represents the NOT gate. So that means we've got A and B or C and D and a NOT gate by the end of the circuit. So that AND gate to that AND gate, that AND gate to that AND gate, and that symbol to that OR gate, and that slope to that NOT gate. So exclusive OR gate or XOR gate, this is the logic symbol or the distinctive shape symbol. Mostly we say the logic symbol of it. So this is going to be A XOR B, and this is going to be the rectangular outline. And this one is, as we said before, the rectangular symbol, which is equal to 1. When you see that one, that means it is an exclusive OR gate. So the logic diagram of an exclusive OR gate is not, that we can't say A exclusive OR directly. So we don't have that one. Instead, the exclusive OR gate is composed of some AND gates and OR gates and even some NOT gates. So in order to generate an exclusive OR gate, you can say for two inputs A, B. So we say A, B complement or A complement B. This is A, B complement or A complement B. This is going to be, the corresponding logic diagram of the exclusive OR gate. When you see that one, you can just directly say it's an exclusive OR gate. A and B are exclusive OR together. And even when you see that, Boolean expression or logic expression, you can say it is A exclusive OR B. This is very important. And so we have two universal gates, which are NAND gate and NOR gates. And they are universal because they can be used in order to generate any other logic circuits or any other logic functions. Let's see why we can do that and how. So this is a NAND gate, right? This is an AND gate and a bubble there. That means it's an AND gate. If you connect those two inputs together, that means whatever the A is, that A is going to be distributed over those two inputs. So if A is 0, the 0 goes there and the 0 goes there. If A is 1, 1 goes there and 1 goes there. That's not a bubble, that's only a connection indicator. So if A is 1, 1 and 1 are going there. 1 and 1 in AND gate is going to be 1, and because of the bubble, which means NAND gate is going to be 0. So if you have A, you will get A complement. If A is 0, 0 in the NAND gate is going to be 0, and in the NOT gate is going to be after the AND gate. So by the NOT gate, or we can say by the whole NAND gate, we will get 1 there. So that means this NAND gate which when both of the inputs are connected together, the result is going to be opposite, or it can be used as a NOT gate. So we can generate a NOT gate using a NAND gate. The same thing if we have two NAND gates together, so we can say we have a NAND gate. How? A and B in the NAND gate is going to be AB complement. So if we connect a NOT gate to it, that means a NAND gate which a NOT gate connected to it. So you will get AB double complement, and those double complement are going to remove each other, and we will have AB. So when we are cascading two NAND gates together, we will get the pure input. So A and B will get an AND gate like this one. So two NAND gates together remove each other, and the result is going to be AND gate. And three NAND gates together are going to generate an OR gate. How? This NAND gate, both of the inputs are connected to each other, and that one as well. So A goes to those two inputs and B goes to those inputs. So A is going to be A complement, B is going to be B complement through the NOT gate. So that means you can see the NOT gate there. So they are NANDed together. That means A complement, NAND B complement, A complement, NAND B complement. So if you apply the Demorgan theorem there, we will get A or B, because that one is going to be broken and the sign is going to be changed to OR, and those two complements are going to remove each other, and the result is going to be OR gate. And if we add a NOT gate by the end of the circuit, we will get NOR gate instead of OR gate. Here we've got OR gate, and here we will get NOR gate, because that NOT gate is going to apply over the whole circuit. So that bar is going to be added to the circuit. So we will get a NOR gate at the end of the circuit. So as the same as the AND gate, we can use the NOR gate in order to implement inverter. How? When we connect those two inputs together, A is going to those two inputs, and if A is 1, so 1 and 1 are going there. In the OR gate, the result is going to be 1, but by the NOR gate, it's going to be 0. So it's going to be complemented. If A is 0, 0, and 0 are going there, and in the OR gate, it is 0, but by the NOR gate, it's going to be 1. So that means a NOR gate, when those two inputs are connected to each other, can be considered as a NOT gate. And if we add a NOR gate when the inputs are connected to each other, so that means it's a NOT gate. So here we have got A NOR B, if you can see that. But this NOT gate is going to revert that one, so it's going to be A or B. So that circuit can be written as this one, as only a NOR gate. If we have three NOR gates, what happens? We can say it's an AND gate, but how? A, B. So this A is connected to those inputs to that NOT gate, so it's going to be A complement, and this one is going to be B complement. And here we have a NOR gate. That means A complement, NOR B complement, A complement, NOR B complement. If you apply Demorgan theorem, that's going to be changed to AND, and that one is going to be broken, and those two NOT gates are going to be removed, and the result will be A, B, A and B. However, if we have four NOT gates, that means the previous circuit, which was up to this one, up to this state, and if you connect a NOT gate by the end of it, the result is going to be opposite to the previous one. So in the previous one, we had A and B, but this one, because of that NOT gate, the result is going to be AB complement, so which is going to be A NAND B, A NAND B. So that's it.